Okay, so let's, I'll start here. Okay, so let me just recap what we did last time and then tell you about what we're going to do today. So what we did last time was we looked at pattern formation in time as opposed to pattern formation in space. So it's one-dimensional, system is uniform, we're just looking in time. And the pattern formation that we're looking at is population cycles and predator-prey ecosystems. And what I showed you was that if you write down the simplest model of that, you get cycles, and that's what you'll see in most textbooks like ecology books. If you go and look at Stephen Strogatz's book on nonlinear dynamics, he'll use that as an example. Okay, and you'll see these cycles. But what I showed you is that those cycles are not the solution to the problem of why you get population cycles, because they're not structurally stable, and they disappear and turn into fixed points as soon as you add the finite carrying capacity of an ecosystem, the ability to support only a finite number population. So then did I do this? I don't remember. Did I talk about? I'm going to have to. Well, I think I did this. Did I show you how you can make a limit cycle by adding the functional response of the organisms? Did I go into that? I have to go back and look at what I wrote in terms of. Yeah, I did. I showed you how you can get limit cycles if you add what's called functional response. But I also explained to you that that's not the solution to the problem, because the problem itself is that the organisms are discrete, and so it's the discreteness that actually matters. And we know this because when you simulate a predator-prey in an ecosystem, and you don't include functional response, they don't worry about how many prey there are. Even just not having that at all, they still get population cycles. So we know that that's what the ecologists did is not the solution. And so then I started at the end of last lecture by talking about how we can understand this stochastically. And the big issue is this. The population is a number which is an integer, but when you have a density, that density is not an integer, it's a real number. So a differential equation for a real number will just keep on going, but a mathematical description that just focuses on the integer numbers of predator and prey, when one of them goes extinct, then the whole ecosystem stops. But the differential equation description doesn't stop. And so we have to find a way to mathematically analyze that. So the end of last time I showed you a method that doesn't work. And today I want to talk about a method that does work, which is the Van Kampen expansion. So we're going to do that, and then we're going to start the last topic, which is using this mathematical framework to study spatially extended systems. And we're going to see that there is a difficulty that we can solve using techniques from quantum field theory, and then we'll use that to look at Turing patterns and the role of stochasticity in Turing patterns. Okay, so what I'm going to start off now is what's called the Van Kampen expansion. And this is a systematic expansion. Whereas the one that I introduced at the end of last lecture was just sort of saying, well, if I take the difference between, I've got n particles, and then I have n+1, so I can think of the difference between n and n+1 as kind of like a derivative, but it isn't really a derivative. We know that it's not a good approximation, so that's not a systematic approximation. and furthermore, if you, by the way, if you do that approximation and you go to higher order, you find that you get negative probabilities and things like this. So it's mathematically an unsound expansion. So the right expansion is the one I'm going to show you now. It's a systematic expansion due to Van Kampen, and it's basically something like the 1 over n expansion that you have in statistical mechanics. So let me write it in a slightly different way. So something like the 1 over n expansion in phase transitions. For those of you who know what that is. Okay, so it's a systematic expansion. What I'm going to show you is at the 0th order gives you the Lotka-Volterra equations that we talked about last time. And then when you go beyond 0th order, so the next order, that gives you the oscillations, the population cycles, and I'm going to show you exactly how they arise in this description. So what we're going to do is the fundamental problem that we have is that we are replacing a number by a density. So the idea is that what is the connection between a number and density. So the Lotka-Volterra equations describe density. The master equation formalism talks about numbers. So what we're going to do is we're going to replace the number, so the ni of t. So this will be the number of species time t. And I'm going to write that as the volume times the density. That would be mean field theory, just an average density. But now what we're going to do is we're going to look at corrections to that, and I'm going to write those corrections. It turns out that the way to do it is a descending power series in square root of volume. So it goes a square root of volume, then a term which I'm going to call psi I, and this is not a fluctuation. This is the this is not a random variable, it's a fluctuation. So it's the variation around the mean density. And then if I were to expand to lower orders, then I have a term of order 1, and then I'd have a term of order 1 over the square root of v, something like that. So this is the kind of asymptotic expansion that we're going to try here. And so then if I rearrange this, that tells me that the density is just ni over v, and then there is a fluctuation term. These are all functions of time, which is down by a factor square root of v, like so. So now the question is, can we derive an equation of motion for the fluctuations? So our goal is derive the equation for the fluctuations around the mean. So here is the strategy. So what we're going to do is we're going to write down the master equation that I've written down for you earlier. So here is a master equation over here on the left-hand side, something like this, just on purple on the left. So that was the form of the master equation, probability for the number of prey, the number of predators at time t, and then there's various terms in that. So what we're going to do is we're going to expand the master equation in an asymptotic expansion in powers of square root of v. And then what we're going to do is equate order by order the terms in powers of v. Order by order the terms in the powers of v. Okay, so that's a strategy. Obviously, I'm not going to go through all the algebra for you. I'm going to just sort of show you roughly what you get, but I'm just going to just sort of show you the key steps of it because it's quite involved to do it all. So basically, the idea then is that we say that the probability of seeing the system with the various n, the occupation numbers of the various species at time t. So I'm going to write that as some new distribution pi of the fluctuations about the mean at time t. So this n here is n1, n2, etc. And in our particular case, it's the number of predators and the number of prey. So it's just like that as a function of time. So that's what I mean by that. So what you find for the equation is this. So dp by dt is d pi by dt minus the square root of v of the sum from I equals a and b of d phi I by dt d pi by d psi I. So that's just by using the chain rule. Now, as I showed you last time, the real master equation back over here has changes in the number occupation numbers by plus or minus 1. So last time I wrote down step operators. So the step operator, so that becomes something like this. So I have one for each species, and that then looks like this: 1 plus or minus 1 over the square root of v d by d psi I plus 1 over 2v d2 by d psi I squared, and so on and so forth. So there's a whole bunch of terms like that. So now I've written down what the step operator is. Then I substitute into the master equation. And look at the different orders. So if I look first of all at order square root of v, then this is what I get, and this is something that's quite straightforward to derive. So the first term is this d phi a by dt is equal to p phi a phi b minus dA phi a, and d phi b by dt is equal to b phi b 1 minus c over b phi b minus p phi a phi b. And if I put in the natural death of the prey, there's also a term like that. So those equations are the Locker-Volterra equations. Previously, I just called them A and B, but now we've recognized that they're actual densities, and so I've written them as phi A, phi B. So we've derived from our stochastic model. So the stochastic model has given us this order. The mean field equation that we wrote down by intuition and you can read off the carrying capacity. So the carrying capacity is equal to B over C, and the birth rate in the Lotka-Volterra is just the birth rate here minus the death rate of the prey. So to summarize, we start off with a differential equation with certain parameters. That's one level of description. The lower level of description is what's actually happening at the individual level to individual creatures when they meet others of the different species and so on. So those have parameters. So those are parameters in the rate equations shown over here on the left. So those parameters on the rate equations turn into the parameters in the mean field equations, and we can easily derive what they are. Okay, so that's mean field theory. Now we want to go to next order. So now when I go to next order, so now I go to order V. So now I get something much more complicated. So let me write it down, and then I'll explain what the terms are. So I get d pi by dt of psi and t. So this equals minus sigma over I and j, a matrix aij d by d psi I. Why does it not manage by I? And then pi times psi j. And then there's another term plus 1/2 sigma ij bij d2 pi by d psi I d psi j. So that's the term. And so this is starting to look like a Fokker-Planck equation. Let me now tell you what the matrices are that come in here. So I've got matrix elements. So I've got two matrices, A and B, and the matrix elements look like this. And again, this is now complicated to derive. So, I mean, it's not impossible, it's just work. So A11 is a minus dA plus P by B. A12 is equal to P by A. A21 is equal to minus P phi B, and A22 is equal to B minus dB minus P phi A minus C phi B squared. And in this one, so I is equal to 1 is the same thing as A, and J is equal to 1 is equal to A. If it's equal to 2, then that implies B. So you can read off what those things are. And then the matrix B, the second matrix, has elements B11 is equal to dA phi A plus P phi A phi B. B12 is equal to B21 is equal to minus P phi A phi B, and B22 is equal to B phi B plus D B phi B plus P phi A phi B plus C phi B squared. So this is just a calculation which I'm sparing you the details of. Now, one thing you can see though straight away is this. These matrices A and B, and I have them now over on the left-hand side. So they're over here. Here's A and B. Those matrices multiply the pi and so on. So those matrices depend on phi A and phi B. So the equation for the fluctuations, the coefficients in that equation depend on the solutions to the equation at the previous order in perturbation theory. So that I want to make this comment then. So at this order in perturbation theory, the coefficients in the Fokker-Planck equation depend on the solutions to the previous order in perturbation theory. So why is that? Why does that matter? That statement is going to be the reason why we say that these equations have multiplicative noise. So all your intuition about what happens when you take equations and add noise to them doesn't work for these equations because they have multiplicative noise. So let's go and see why. So this has a very strong implications for the associated Langevin equation. So this is an equation. So what I've derived here is a differential equation for the, over here on the bottom in pink, a differential equation for the probability distribution. Okay, this is the Fokker-Planck equation. It's a differential equation. And every Fokker-Planck equation has a Langevin equation associated with it. So we've gone from master equation, which describes discreteness, to a Fokker-Planck equation, which is an approximation to the discreteness. And now we're going to look at the Langevin equation, that if I started with that Langevin equation and did the calculation I showed you in the first part of this this part of the course, you could derive the Fokker-Planck equation. So that Langevin equation is going to have a very specific structure. So this is going to be, this has very strong implications for the associated Langevin equation. Remember, the Langevin equation is like the equation of motion for a variable. Here is a position, it is fluctuating. I write its position as a force plus a fluctuating term. Then I can work out an equation for the probability distribution of its position. That's the Fokker-Planck equation. And then taking into account the discreteness gives me the master equation. So let me write down for you what is the associated Langevin equation. So here's what it looks like. It looks like this, d psi by dt. So this is the derivative of the fluctuations. There's some matrix that depends on psi plus some noise, which I'm writing as gamma. So this is the deterministic part. And this thing over here, this is the noise, and the noise satisfies the following: gamma, oops, symbol, gamma I on average is equal to 0, but if I look at the correlation function, gamma I of t, gamma j of t prime, then that, when you work it out, goes like this. It goes like bij delta of t minus t prime. So you have noise that is delta function correlated Gaussian white noise, but the coefficient of that is the matrix B, and that matrix B has matrix elements shown over here. And those matrix elements depend on the previous order of perturbation theory. So the fluctuations, their correlator depends on the average value. If the average value goes to 0, then the fluctuations, then the correlation of the gammas also goes to 0 as well. So roughly speaking, this equation is of the form d, some variable d psi by dt is equal to something times psi plus something that is the square root of psi times a white noise. That's the structure of this equation. So the B, remember, is linear in the phi's. So if I then work out what the noise itself is, it's going to be the square root of that. And so what we've got here is, if this is psi is the density, then we have the noise multiplied by the square root of the density. And so what happens is, if the numbers go to 0, then this equation will stop working. So this equation, the fact that when psi is equal to 0, the noise does not excite the equation, means that psi is equal to 0 is an absorbing state. So in other words, once you get to psi is equal to 0, then the time evolution stops. And that's the thing that comes from the fact that this is an equation for integers. So what we've done by this is we've now represented in a stochastic differential equation. In fact, it's going to be a PDE. We've represented a stochastic PDE, the discreteness of the population. And that's the thing that we couldn't do before. Okay, so that's how this works. You have to just do the mathematics to see. If you want to learn how to do this, you just have to do the calculation. Yep.
So is B equals 0 by regular Gaussian noise, like with a constant amplitude?
So B is just a matrix or numbers, or that depends on the average density.
So if it's like, let's say the A matrix is 0 and B is independent of phi, the mean density, and I solve for like pi of C.
So remember that the correlator goes like B. So the noise here, when I'm drawing it, that gamma then goes like the square root of B.
Yeah.
And so B itself goes like, has got terms which are linear in phi. And so roughly speaking, I mean, it's more complicated in a matrix sense, but roughly speaking, the square root of the density is the thing that multiplies the Gaussian white noise.
But if I solve for that Fokker-Planck equation, dou T pi equals D, dou square x, it's a heat equation. So over time,
it doesn't do that. It doesn't, because of this, because the noise is multiplicative. Because you have to solve both orders simultaneously.
Oh, so I have to like.
So it's not like phi is given. Phi is given by solving the previous order in perturbation theory. So you have to do this order by order in perturbation theory, and and this is an asymptotic statement. If I were to write this down in the language of, say, the Kramers-Moyal expansion, which I showed you last time, you would literally end up with the equation shown here in the middle of the page. That you literally have a stochastic equation where the white noise is multiplied by the square root of the variable that you're solving for. So this is how for asymptotically large n perturbation theory, you represent a multiplicative process.
So if I had to solve for pi, I had to solve for phi and then put it back here,
yeah,
and then I'll get a stationary pi.
Yep. And so the equation will stop evolving when it goes extinct. So this equation with multiplicative noise is able to capture extinction and all these discrete events, as I'm going to show you. Okay, so I mean, you know, how it does it is I'm sketching it for you. So the next question is, what do we compute? And so my answer to that is what we're going to do is we're going to compute, we're going to solve the Langevin equation. But now what is happening? Does this thing just, how do I get back? Am I still online? Am I still recording? I'm showing, hopefully everybody can, hopefully it's still recording, and hopefully Cindy, who's online, can see what we're doing. Cindy, can you hear? Can you see my screen?
Yeah, I can see everything.
Great, perfect. Okay, so what do we compute? So what we're going to do is I'm going to show you how to solve the Langevin equation by a Fourier analysis. There's more complicated ways to do it using what's called Martin-Sidger-Rose formalism. I'm going to just show you a quick and dirty way to do this. So what we're going to do is we're going to assume that the system is in a non-equilibrium steady state. And so I can just take a Fourier transform. So my variable psi of t, which is the fluctuation about the mean, which has a deterministic part and a stochastic part, and it's a vector, one for the predator, one for the prey. So I'm going to write that as in terms of its Fourier transform, psi of omega, like so. And the Langevin equation is then going to have the following form: minus I omega psi is equal to this matrix A times psi hat plus gamma hat of omega, and the Fourier transform of the noise looks like this. So really, you should think of this, the only non-zero part of this is when omega prime is equal to minus omega. So that's what this equation looks like. So then what I want to compute is the power spectrum. So what is the power spectrum? It's basically an autocorrelation function in time. So I'm going to define it like this: Pij of omega is equal to psi I of omega, psi j hat of minus omega. Like that, that's the power spectrum. And notice that my variable is real. So if I have a real variable psi of t, then for that the Fourier transform complex conjugate is equal to is equal to psi hat of minus omega. Okay, so if I have a real variable, its Fourier transform in frequency space, it's taking the complex conjugate of that is just the Fourier component in minus omega. And so when you calculate that, so now you just calculate. And how do I calculate? Well, I've already got the algebraic equation for psi. So here's my algebraic equation. So I literally just write down what P is and do the average. And so that you can find out that it looks like this. P11 of omega, I'm just going to write down one of the components is alpha plus beta omega squared over omega squared minus a variable called big omega, which I'll define in a minute, plus gamma squared omega squared. Okay, so that's just P11, the power spectrum, or the autocorrelation of the predator with it itself. And now I need to tell you what these coefficients are. So here, so alpha is equal to B11 times A22 squared plus B22 A12 squared. Beta is equal to B11. This number omega squared, which is obviously going to be a frequency, is 2p squared phi A phi B, and gamma is equal to minus A11 minus A22. Okay, so we've now calculated the power spectrum. So what? How do we interpret it? So now let's discuss the interpretation. Now, some of you should be thinking, I've seen something like that before. And you have. So what I'm going to show you is that that this is a damped harmonic oscillator. And we're going to see that the natural frequency of the oscillations is big omega, and then there's a damping that comes from gamma. So let's have a look and see what I mean by that. So let me show you how that comes about. So to see this, consider this example. So I'm going to think of two variables, x and t and y of t, and they obey the following equation. So x dot is equal to a11x plus a12y plus gamma of t, and the gamma is a noise, and y dot is equal to a21x plus a22y plus gamma 2 of t. So the gammas are the noises. Okay, so let's just look and see how we would try to solve this equation. So what would we do was we'd say, okay, well, I've got x and y. So the idea would be eliminate y in terms of x. So how would you go about do that? And let me just ignore noise. So eliminate y in terms of x. and then differentiate to give a single equation So let's just see how we would do that. So if I take the x equation and differentiate that, that looks like x double dot is a11 x dot plus a12 y dot. So that's true. Now I can substitute in the equation for y dot. So that is then a12 x dot plus a12 a21x plus a21 y. But then I also know that y dot, sorry, I know that y is equal to x dot minus a11x over a12. And so that means I can write this whole thing as x double dot is equal to a11x plus a12 a21 x plus a21 x dot minus a11x. And so in other words, what I end up with is x double dot plus x dot minus a11 minus a21 plus x a11 a21 minus a12 a21 is equal to 0. And so this is a damped harmonic oscillator. So if I look at the equation that we have, that I've derived for you already on the left-hand panel, that equation is of the form of a damped harmonic oscillator. So that that power spectrum will have, if I just simply multiply that out, it will look like the power spectrum on the right, and so the deterministic parts of this look like a damped harmonic oscillator. So we still have to add in the noise. So when you add in the noise, what happens is that you get extra terms on the right-hand side that drive the damped harmonic oscillator. And I'm not going to write them out in detail for you. So I've got a damped harmonic oscillator, but it's being driven. So when a damped harmonic oscillator is being driven, it is going to sort of oscillate and then decay, and then it gets kicked again, and then the amplitude grows, and then it decays, and it gets kicked again and grows and decays. So that's how you get the persistent oscillations. So the noise on the right-hand side of the damped harmonic oscillator is a white noise. If you calculated its properties, but it's not like that because we assumed it, but because we calculated it. We calculated it in a principled way. Okay, so what I did, of course, I've just gone over it very carefully, but all of this can be done carefully and can be made rigorous. Okay, so now here's the thing. I've got a damped harmonic oscillator. Okay, it has a particular frequency. It's got a natural frequency. It is being driven by what? By some sort of white noise. That white noise is going to excite all the frequencies. So the white noise will excite all the frequencies because it's white noise. But the ones that get excited the most, the ones that are most responsive, are frequencies near the natural frequency of the harmonic oscillator. Again, that's not something that we've assumed, we've calculated that. So if I look at the power spectrum, this is what it's going to look like. This is just the P11. So what it looks like is this. Oh, actually, let me just keep this color for a moment. So here is the frequency omega, which is the thing that we've calculated. That's the natural frequency. And then the power spectrum looks something like this. So I'm probably going to draw a crappy job, but something like that. Something like that. So that's what P of omega looks like. And if you look at the formula that I have over here, so this looks like alpha plus omega squared, and then it's divided by omega squared minus capital omega squared. So now you can see that this capital omega here, that is the natural frequency. You can see that this gamma here is the damping, and you can see that in the numerator it's omega squared. The denominator is omega squared squared, which is omega to the fourth. So what that means is that this tail over here, that is going to have an omega to the -2 tail. So there's a long range correlation in the power spectrum that you get from these number fluctuations. So this is the form of the power spectrum. So omega is the resonant frequency. And then gamma is the damping. So if I look at this power spectrum, if I had no damping, this power spectrum would just be a delta function at capital omega. So the width of this power spectrum is somehow related to gamma. And again, these are things that we've calculated just from our microscopic level of description, which are the rate equations for this predator-prey system. So what actually happens in this system, if I gave you a simple harmonic oscillator with damping, the first thing you would ask yourself is, well, what is the Q factor? Okay, so if the Q factor is very high, then you get a resonance. The high amplitude peak in the power spectrum omega, and you can calculate that, and it turns out that it is a high Q factor, and so you get a resonance that gives rise to the oscillations. So this actually can be so this means that you get population cycles due to the stochasticity arising from the underlying discreteness of the population. So that's the first thing, that's where it comes from. And then the reason that you can observe it is that the stochasticity is amplified by a resonance And then the last thing I want to tell you is that this stochasticity can lead to extinction. So let's have a look at the phase space of this system. So I'm going to look here. This is going to be A, and this is going to be B. And I'm going to look at it in two different ways. So this is A and B. So on the left picture, here's what I want to draw. I want to draw what happens when I have the Lotka-Volterra equations when the carrying capacity is equal to infinity. So what we would expect classically is that we would have a center, something like that. So that's the deterministic one, the deterministic solution. If I then compute the stochastic solution, what happens is it's going to be doing something like this. But now the stochasticity will actually violate the conserved quantity that gives rise to the centers that we talked about last time. How did that happen? What the heck? I mean, is this AI? This thing is more smarter than me. It's not smarter than me because what happens is eventually this thing will wander off and eventually it will go extinct like that. So that's what happens if I use the Lotka-Volterra equation with infinite carrier capacity. Now, what we know for the Lotka-Volterra with kappa less than infinity. So now we know that there's a fixed point. So we never get population cycles. It just goes into some fixed point. And if I were to look at the if I were to look at the trajectory, as I showed you last time, the trajectory kind of spirals in like that. So that would be the deterministic case spiraling into this fixed point. Now, what does the stochastic theory look like? The stochastic theory looks like this. It starts off like this, spiraling in, but then some event happens. Some event happens, and then it jumps out to over here. Then it starts to spiral in again, and then a birth-death event happens, and it jumps to over here. Then it spirals in, and then some event happens, and it jumps out to here. Then it goes like that. So what's happening is this thing is falling in towards the deterministic fixed point, then being kicked out by the shock noise that comes from the discreteness of the population. So this is what the trajectory looks like. This is why you get persistent oscillations. Now, just as I said before, you can have extinction. So eventually, these trajectories might evolve and go around and say hit one of the axes like that, and then you would get extinction. So once you have stochastic, events, you always have a finite probability of the system going extinct. The bigger is the system, the smaller is the probability. These have become exponentially rare events, so they can keep going for millions of years, but eventually, mathematically, these sorts of equations will always have extinction. All right. So give me 1 second, and I want to finish this, and then I'll take the question. Okay. So let me now make a couple of comments. So comments. So in this calculation, I took the control volume of the system to be V, and so what we did was we did an expansion in V. Or literally 1 over V. So there's no spatial variation here. We still have in V a fixed volume. Well, does this apply to a real system? The answer is definitely not. Okay, it definitely doesn't, because we have the real system looking like this. We have our predators sort of floating around like so. We have our prey floating around like this, and clearly there is a heterogeneity in this population. So what we will actually need to do is we actually need to generalize to a non-uniform distribution, predator and prey. And if I do that, then this volume becomes something like a correlation volume. So we need to look at the spatial variation. In order to even be able to interpret this calculation, we have to do the whole thing with space. So this the calculation that I've shown you here was first done by McCain and Newman. They did it in a different way than the way I presented it. This was in a PRL from 2005, and these are population cycles are known as quasi-cycles. To correctly interpret this whole thing, you have to actually then redo the whole calculation in a spatially extended way. And I'm going to show you how to do that. Now, if you read their paper, it's a very beautiful paper. I encourage you to read it if you're interested. They do it in a different way than the way I did it. The way I did it was I put the carrying capacity in as competition between the species. But another way you can do it is what's called an urn model. You just say, here are lattices, there's a finite number of lattice sites, and things hop around on the lattice. So you have a hard constraint there, rather than the soft constraint that comes from the competition that I put in. So the calculation is technically, the algebra is a bit messier, but that's how you can do it. So that's the first thing. That's paper. There are other precursors to this paper, but this is the presentation that I think was the first one that really understood what was going on. And then, if you want to know about the extinction, so the question you might want to ask is how long does it take? And the answer to that was provided by Reichenbach, Mobilia, and Fry in a paper from PhysRev E 2006. and there's other papers. And you can calculate how many cycles, population cycles you have to go, how many periods you have to go before the thing has got a non-zero probability of extinction. Okay, so now I want to go on. So now we have to do space. So now I'm going to start space. We're not going to finish space today, but we're going to now put in space. So the next thing that we're going to do is we're going to include space. And if you just take space and add it to the predator-prey equations that I've just showed you, the result is incredibly boring. Okay, you do all this work, and if you do it the way that it was originally done, it really is a lot of work. It's really, really annoying calculation to get right. And once you've got it right, there's nothing interesting in the calculation at all that I can see. So apart from just sort of calculation and correlation volume. But now I'm going to show you what happens if you do a slightly different model. And I'm going to tweak the predator-prey model, and we're going to tweak it in a way that relates to what happens in marine algae. And this tweak that we're going to do is going to introduce a Turing instability to the problem. And what we're going to see is that when we include a Turing instability, then amazing things happen. It really becomes fantastically interesting. So the next thing we're going to do is we're going to include space. But what we're going to do is we're going to specifically look at stochastic Turing patterns. And so what my goal is in this section is, first of all, I want to review the intuition of Turing patterns. And then I'm going to, in particular, I'm going to introduce a model of patchy plankton in the ocean, and we're going to look at plankton that is being eaten by some herbivore. And we're going to see that this model has a Turing instability. To form patches. And then we're going to see that they are hard to observe. And then lastly, what we're going to do is I'm going to tell you why they're hard to observe, and we're going to see the profound effect of noise coming from demographic stochasticity. Now, what we saw in the predator-prey system was that when we had the deterministic solution, we did not get population cycles. We did not have a pattern in time. We just had a fixed point. When we included noise coming from the discreteness of the individuals, that then created a pattern in time. It created persistent cycles with a particular frequency. So the pattern was actually stabilized by noise. The pattern in time was stabilized by noise. So when I talk about the profound effect of noise coming from it, we've already seen a preview of that here. In our predator-prey calculation, what we saw was that the deterministic finite carrying capacity calculation had no cycles, i.e. no pattern, but the discreteness gave stochasticity, which we calculated, which gave cycles, i.e. patterns in time. So the bottom line of the calculations I just outlined for you was that noise or discreteness stabilizes patterns. And this is a very profound effect. So let me show you how we go about doing that. So what I'm going to do, what I should have time to finish today, is I want to give you the physical intuition of the Turing pattern. Then next time I'm going to mathematize it. And I'm going to show you how you do the calculation. So let me set up set up the problem. So Turing, this is in 1953 or something like this. This is the same Turing who invented computers and things like this. So he wanted to understand, why do you have patterns in nature? Why do you have stripes on, what has stripes? Zebras, spots on what has spots? Cheetahs or something? Leopards? Okay, leopard gets a spot, yeah, things like that. So he wanted to know, so he had this idea, well, you've got some chemicals that diffuse around during development, and they diffuse, but they can have some instability that breaks translational invariance in space, and then you get these patterns. So that was his idea. It was, in fact, it was completely wrong, okay? But, and you guys know this even better than I do, but it's completely wrong, but it did launch this era of trying to understand the pattern formation. It's completely wrong because it doesn't take into account differentiation. It doesn't take into account genetics, all sorts of things like that. But it has a role at play for sure. So here is the idea. So we're going to consider predator and prey as before. I'll call them A and B. But what we can do now is that they are allowed to diffuse. So they have a diffusion coefficient dA and a diffusion coefficient B. And in general, if you're thinking about them ecologically, you would say predator and prey. If you were thinking about them in, say, a chemical reaction, you might call the predator the inhibitor, and the prey the activator. And so we're going to use that notation, and you can see why the predator goes and eats the prey, so it inhibits the population of the prey. It stops it growing. So we're going to say that they have these diffusion coefficients, and what we're going to find is that there's a constraint on these diffusion coefficients in order for a pattern to form. And we're going to see that constraint is completely unrealistic. It virtually never is satisfied in any natural system. That's another reason why Turing's idea didn't turn out to be as profitable as he thought. Now, let's talk about what these activators do. What the activator does is it catalyzes its own production. It also catalyzes the inhibitor production. So that's what the activator does. What the inhibitor does so the inhibitor reduces its own concentration and that of the activator. So that's what that's what we mean by activation and inhibition. And in fact, you need both of these things are needed in order to get pattern formation. Okay, so let's walk through how this actually happens. So what I'm going to do is I'm going to draw for you some spatial profiles of the system, and then I'm going to show you what the time evolution is, not just knowing nothing about these things, other than the fact that they diffuse around, and the fact that that they have the property of activating and inhibiting. I didn't answer your question, did I? Sorry.
It got resolved in the comments, so.
What?
It made sense when you.
So I answered in the comment.
Yeah.
Okay, great. Yeah, that's actually why I was hoping to give the comment and let's see if you still need to ask a question. Okay, so what we're going to do then, so our strategy for now is just sort of cartoon picture of the time evolution of the system. And then next time we will mathematize it. So I'll try to number these steps so we can refer to them later, but I'll probably forget, knowing me. So step one. So I'm going to assume that say I'm looking at B as a function of space. The X now is the horizontal axis of space. So I've got some distribution that looks like something like this. Okay, so that's what it looks like at time at t equals 0, and this is B. This is the activator I'm drawing here. So what's going to happen at later times? So at later time, what's going to happen is the local region where B is higher is going to grow faster because there's more of the activator there. So what's going to happen is this thing is going to look something like this, but this region is going to have grown particularly more like that. So this is what I would expect for t greater than 0. So what would I expect for the to happen next? So here I'm going to do again B. So this is step 2. So far I've just talked about reaction. Okay, so that's all I've talked about here is reaction. Now I want to talk about diffusion. So these equations that we're going to write down are generically called reaction diffusion equations because they involve reaction and diffusion. So the reaction is the description on the left-hand side of what an activator and inhibitor is. The diffusion is what I'm about to explain right now. So now let's take our profile that we just described, that we just derived. So I'm going to say something like that. So that's what I got. And then now I'm going to ask what happens if I go further in time. So what's going to happen is it's going to diffuse out. So it's going to actually sort of look, I don't know, so something like this. So the prey has now diffused. So I get that. All right. So that's step 2. Now let's do step 3. So I'm going to draw, now I'm going to draw the predator and the prey here. So what I should do is let me just do this in a low-tech way. So here's what I've just shown you. So there's my time. Then I have the diffusion like that. And now let's add to this the predator. So what is the predator going to do? The predator is activated by the prey. So if the prey population is the purple one, then now what's going to happen is the predator is going to be mostly in these areas, something like that. So this is going to be the predator now catalyzed by the prey. Okay, so that's step 3. But the other thing that happens is that the predator moves, has a higher diffusion constant than the prey. So what it's going to do is it's going to run around and eat up the prey on the edge. So now the prey population is going to look something like this. So that's now the prey, and what's happened here is that the rapidly moving predator stopped the diffusion of the prey. So that's what that looks like, and then the predator itself is still something like that, and then what's going to happen is the predator. So that's step 4, and then the last thing is step 5. So now what's going to happen is I've got my prey like this. And now the predator is going to inhibit itself. And so its population is going to go down like this. So here the predator has inhibited itself. And does not overwhelm. Right. So I've now got a patch. And so the end result is all of this gives me a patch in space of prey surrounded by predator. And so I've got spots. And that is the start of the pattern formation process. So you can imagine that if I was doing this with some, spatially random initial condition, I'm going to end up with a bunch of patterns. So this is the start of the pattern formation process. Okay. All right. So the last thing I want to say is this, and then we'll leave it for today. So the first comment is that if I have a regular predator-prey model, that has no predator competition. So that means that the predator does not inhibit itself. So the regular predator-prey model isn't an example of this. And so we have to extend the model to include predator competition. So we'll do that next time. And I'll show you how we're going to make a mathematical model of this. And then we're going to actually end up using, I'm going to very superficially show you how we use second quantization to turn this thing into a field theory and then calculate what happens in that case. Again, using the same dirty tricks that we did before. Okay, so that's today's lecture. So let me stop the recording.